Hello. In this video, we're going to practice finding the area between curves. For this first example, we want to find the area bounded by 4x plus y squared equals 12 and x equals y. So if we look at these curves, we can see that the first one could be written in terms of x or y, and the second one could be written in terms of x or y. But let's look at that first curve and actually solve it for x equals. So if we move the y squared over, we'll have 4x equals 12 minus y squared. And dividing through by 4, we'll have x equals 3 minus 1/4 y squared. Of course, our other curve is still x equals y. Now, although this may seem more complicated at first, having our curve x equals was relatively easy to isolate. If we had to solve for y, we would have to take the square root and look at both the positive and negative square root. Instead, it's easier to just isolate for x equals. Now, what this means is it's not our regular function. So when we go to graph the function on the axis, it's going to be a function in y, not a function in x. So looking at this curve here, we can identify it as a parabola. It's opening down, and it has the vertex shifted up at 3. So we can graph that as follows. We will have our vertex here at about 3. And our parabola will open downward. In this case, it will open left, something like that. And the other curve, x equals y, will simply be a straight line through the origin. So this here is the blue, and this is the red graph. So wanting to find the area, we're going to need to find these 2 points of intersection. To do that algebraically, we simply set the two equations equal to each other. So we have y equals 3 minus 1/4 y squared. If we move everything to the left-hand side, we'll have 1/4 y squared plus y minus 3 equals 0. Multiplying through by 4, or we could factor out the quarter, will give us y squared plus 4y. Subtract 12 equals 0. And factoring will give us y minus 2 and y plus 6 equals 0. The first factor will give us y equals 2, and the second will give us y equals negative 6. And we can see here from the graph that that looks reasonable. We have the first intersection point down here at about y being negative 6. Then we have the second point up there at y being positive 2. Again, if you sort of turn your paper to the side, you can see that this red curve here is going to be the upper curve, whereas the blue curve here is the lower curve. So when we set up our integral, it will be as follows. So we will have the integral from y equals negative 6 to y equals 2 of, and our upper curve will be 3 minus 1/4 y squared, and our lower curve will be minus y dy. So to integrate that, each term, we can use the power rules. So we will have 3y minus 1/12 y to the 3 minus y squared over 2, evaluated from negative 6 to 2. So if you work through all of the algebra and arithmetic, you should get the following answer: 64/3. Now, taking a look at one last example here, we have the following problem. consider the area bounded by x equals y squared and x equals 4. We want to find an A such that the line x equals A splits the area into two parts. Now, let's think about that for a second. Let's go ahead and draw a quick sketch of our curves. We have the first one, x equals y squared, so that will be a parabola opening to the right. And we have the line here, so that's our first curve. We have our second curve, x equals 4, so that would be a vertical line. We want to find some number A, so we're looking for some number A here. Some number A such that x equals A, if we were to cut that shape right there, the area on the one side would be equal to the area on the other side. So it's not initially clear how to do this problem, and I think the first thing we should do is we should figure out, overall, before we try to cut the shape in half, this area total, what is the area we're working with to start? So we should calculate that area, and that means we're going to need to find our intersection. We're going to need to find this point up here and this point down there. Well, of course, we have y squared equals 4. That means y equals plus or minus 2. So our points of intersection are minus 2 and 2. The blue line is our upper curve, and the red line is our lower curve, so we will have the integral from minus 2 to 2 of 4 being the upper curve, and y squared being the lower curve, dy. In this case, we can evaluate this quite easily as 4y minus y to the 3 over 3 from negative 2 to 2, which will give us 8 minus 8 over 3 when we plug in positive 2. And we subtract negative 8 plus 8 over 3 when we plug in negative 2. And working all of that out, we should get 32 over 3. So what that means is, looking back at our shape here, the area between that blue line and the red parabola, that total area there is 32 over 3. Now, we want to find this A that splits the area. And so we want the new area. We want the new area, the area with the point A, to equal half of what we started with, or 16 over 3. That's what we want. We want that to happen. Well, the way we would write that is as follows. If that's what we want the area to be, well, we have to have 16 over 3 equal some integral. Now, in this case, we're going to integrate x equals A will be our upper curve, and the red parabola will still be our lower curve. So we'll be integrating along that parabola, trying to find where those points of intersection are. Well, looking back when we solved the first time, originally we had y squared equals 4, so y was equal to plus or minus 2. In this case, y squared will equal A, because we're trying to find where the parabola and that purple dotted line will intersect. And so that means we can write here, y squared will equal A, or y will equal plus or minus root A. So the bounds on my integral will be from minus root A to root A. of a is the upper curve, and y squared is the lower curve, dy. So this is the equation that I want to be true. I want that to happen. I want this integral from negative root a to root a. I want that to give me 16 over 3. So the way I can do that is actually evaluate the integral. So here I will get a times y minus y cubed over 3 evaluated from negative root a to root a. So let's continue here. I want to plug in this top value and then subtract the bottom value. So I will get a root a minus root a cubed over 3 subtract a negative root a subtract negative root a cubed over 3. Now we're going to have to be careful with our signs, but we can clean up this right-hand side. So this will be a to the 3 over 2 minus, and square root of a all cubed will be a to the 3 over 2 over 3. Subtract, and since we're subtracting a negative, we'll get plus a to the 3 over 2. And here we're going to have a negative and a negative and a negative. And so we will have subtract a to the 3 over 2 over 3, which can be combined to give us 2a to the 3 over 2 minus 2a to the 3 over 2 over 3, which equals, finding common denominator of 3, this will be 4 over 3, a to the 3 over 2. And we know that we want this to equal, this integral should equal 16 over 3, half of our area. So now we want to rearrange and solve for a. This will give us 4a to the 3 over 2 equals 16. And so a to the 3 over 2 equals 4. And so a will equal 4 to the 2 over 3, which is just a number. If you want, its a is equal to the cube root of 16. And for homework, you can take that value of a, and you can actually plug it into the integral here, and see that you do indeed get 16 over 3. Again, for homework, please try the following questions. Thanks for watching.